Okay, so the next problem I want to look at is from 2015, from the first midterm, problem 4. Okay. So I want to take a look at this problem because it's an application of the superposition principle and it involves dipoles, so that's something that we can look at. So there is a figure that I'm not going to try to really reproduce here, but I'm going to draw a coordinate system. So this is Z, X, and Y, and there's a plane of charge in two planes. So there's one in the XY plane, and there's one in the XZ plane, and there's one in the YZ plane. Okay, so the one in the YZ plane is sigma 1. It has a surface charge density of sigma 1. That's 70.8 microcoulombs per meter square. And the one in the XZ plane is sigma 2, which is minus 53.1 microcoulomb per square meters. Okay? And we have a dipole of dipole moment P equals 200 microcoulomb meters. Its position is at P. So this is at 110 meters. So X equals 1 meter, Y equals 1 meter, Z equals 0 meters. So it's somewhere in the XY plane, some distance from the Z-axis. And they're telling us to notice that the 7.8 is 8 times 8.85, and 53.1 is 6 times 8.85. So perhaps write this down. This is 8 times 8.85, and this is 6 times 8.85. And they are giving you the epsilon naught numerical value, 8.85, and hence the simplification algebra, I suppose. It's 12 coulomb square per Newton meter square. Okay. Now, the first task is to find the electric field at the position of the dipole, and we are asked to express our answer in terms of the unit vectors. So the electric field, part A, is the electric field at P. Right, so how would you find this? Now, this is, as I said, an example of superposition. So these two planes are going to produce some electric field. And we can think of these, because these are, we are given the charge densities, not the total charge or anything like that. We are told that these are uniform. We can forget about one and calculate the electric field due to one, and then do the same for the other, and just add these up. Okay? If these were conductors, and if the charges were responding to the presence of other charges, you couldn't do that. Right? Obviously, these are insulators, because these charges remain uniform in the presence of other charges. So we can calculate the electric field at point P as the electric field produced by the first plate at point P plus the electric field produced by the second plate at point P. Okay? And the electric field produced by the first plane, so the first plane is the one in YZ plane. Okay? So this is going to produce at this point P something in the positive X direction. And it's going to be, so the electric field produced by a plane of charge is sigma over 2 epsilon naught. So this is going to be sigma 1 over 2 epsilon naught in I hat. Okay? That's what we produce. And the other one is going to produce sigma 2 by 2 epsilon naught. By 2 epsilon naught. This time it's going to be in the positive y direction. This is just j hat. Okay? And when you plug the numbers in, it's going to be something simple. So 70.8 divided by 8.85 is going to be 8 divided by a further 2. It's going to be just 4. Okay? So this is 4. Now what about the units? This is microcoulombs per meter square. This is Coulomb square per Newton meter square. Well, you need to figure this out. I'm not going to do this, but it's 4 I had plus sigma 2 is minus 6 times 8.85 divided by 8.85. You just get the 6, and then it's a negative sign, so it's minus 3 J hat. Yeah. But there's something additional. So there's a 10 to the 12 coming from here. It's in denominator, so moving to numerator, it becomes 10 to the 12. And we also have to write the units. Okay, actually, I can look this up. Yes, so the units are Newton coulombs. And it's 10 to the 6 Newton coulombs. Okay. You should, however, get this number yourself and then check whether you got it correct or not. Okay, so for part B, they're asking, find the torque that the electric field exerts on the dipole. Express your answer in terms of unit vectors. Okay, so we have a dipole that looks, are they giving me direction? It's oriented in the positive z direction, so P is parallel to K hat. Okay? That's the other thing they are giving me. So this means that if I write the P as a vector, it's going to be 2 microcoulombs meters K hat, something like this. Okay? Now I'm going to erase all of this to make room for the new calculation. Maybe I keep just these two. Now the torque that's produced is going to be P cross E. Now first of all, yeah, this is not something simple. You can't easily draw the direction of the electric field here, so I'm not going to try to get a sense of what this would look like. But here you have to take a cross product. Okay, so you have to take a cross product of this. So P K hat cross. This has x and y components, Ex I hat plus Ey j hat. Okay? And the way to do that is to distribute this cross product over the terms. So this is going to be P Ex K cross I hat plus P Ey K cross j hat. Okay? And then you need to recall the rule for cross product. So I cross j gives k, and if you flip these two, then you pick up a negative sign here, and the cyclic permutations of this is also correct. So if I move this over here, I'm going to get j cross k is equal to I hat, and if I move once more, k cross I is j hat. Okay? So k cross I is j hat, this is j hat, and k cross j, we don't have that, but j cross k is I, so this must be minus I hat. Okay? And recall that this is already minus, so this minus minus is going to be something positive. Then they are asking how much work is done by the electric field on the dipole until it's aligned with the electric field. So currently it's not aligned. The electric field is pointing in some x and y direction. This is pointing in some z direction. So if we rotate this, how much work is going to be done? Now, to do that, you have to recall the definition of work done from mechanics. And the work done, part C, is the change in potential energy with the negative sign. Okay? You could also, of course, remember that this is the work done is the line integral of the force over some path, and the force is the gradient of the minus potential energy and so on and so forth, but this is something hopefully you can recall. And if that's the case, then we have to calculate the final kinetic potential energy and the initial potential energy. So when it's aligned, so the potential energy is given by minus P dot E. When it's aligned, these are going to be in the same direction, so this just gives minus PE. Okay? So this is the, let's just write it this way. The initial potential energy requires you taking the dot product honestly, but so what does this look like? So minus P, what was this, K hat dot product with EX I hat plus EY J hat. Okay? And again, you can distribute the dot product over this, but K dot I or K hat dot I hat is just going to be 0. They are two orthogonal vectors. K dot J hat is also going to be 0 because they are orthogonal vectors, so this is going to be 0. So the change in the potential energy is just going to be P times E, okay? Or minus P times E. So it's going to be a negative number, and the work done is going to be P times E. Okay. So I guess I should mention one thing. So it is P times E, yes, but what is E? Well, E is the magnitude of the electric field. So as such, it is just EX squared plus EY squared square root. Okay? So we all know these components. It's those 3 and 4 times 10 to 6 business. And you just need to calculate this. So this is just going to give you 5, right? The 3, 4, 5 triangle. You can easily calculate this. And this P is something that's given in the problem. I think it was 2 microcoulomb meters, something like that.